Hello everyone, this video will be about using SPSS for regression analysis, and we'll kind of go through an example we went through in class first. And in this case we have some information on individual salary, their age, and their education level, and we want to use that data to predict, well, we want to use age and education level to predict their salary. All right, so when we talk about regression, and use the term generically, usually we're talking about what we call ordinary least squares regression, or OLS as I often call it. With OLS, there are certain constraints that you have, and we haven't really talked about all of them in the class because some of them are kind of complicated. But as a general rule, your dependent variable needs to be interval or ratio level measurement. You do not want to use OLS regression to predict a nominal variable. Right? There are reasons for that, which we or an ordinal variable, and there are reasons for that we talked about in class. So keep that in mind. We have logistic regression and other types of regression that works in those cases. So we can still do those sorts of analyses, but not with kind of what we call linear or OLS regression, ordinary least squares. OLS, by the way, just ordinary least squares is how it fits a line. If you're thinking about a regression in a scatter plot between two variables, fitting a line to that scatter plot to give you the slope for the regression equation, how it does that mathematically using ordinary least squares is what that means. We haven't really talked about what that really looks like because it's not tremendously important. So I could do kind of a regular regression here, OLS regression. You go to regression linear, and I'm just going to do a very basic one. I'm going to predict salary with age. This is also what we might call bivariate or simple or OLS regression because we only have one independent variable. We'll add some more in a few minutes. At the end of the day, it doesn't really matter. It does affect the math a little bit, but we're not going to see that. It does affect the interpretation, but only in a minor way. So it's not tremendously important whether we're talking about simple or multiple ordinary least squares regression. So I use age to predict salary. And we've done this one in class. I get R squared 27.6, telling me that age explains about 27.6% of the variation in salary. Hey, people's salaries vary. Age can explain it. It's not saying age is causing it. It's saying age can be used to explain or predict it. And of course, we do want to predict someone's salary with their age. We'll use the coefficients below. You can see we have a constant or y-intercept of about $17,593. We would take that, and then we would add to that the product of $519 if we round times the person's age. So if someone was 30, we would multiply 30 times $519, get that figure, and then add that to the y-intercept of the constant of $17,593. That would give us a prediction of the individual salary. It's not going to be extremely accurate because our R square isn't that high, right? The higher the R square, the more accurate your predictions are going to be. But we only have one independent variable, age. So often with one independent variable, you're not going to get that high of R square. Dependent variable, of course, is salary. So this is pretty straightforward. The only thing we look at is I didn't ask for confidence intervals. One thing I don't like about SPSS is when you run regression, if you want the confidence intervals for the coefficients, you have to go to statistics, confidence intervals. 95% is the default. You can change those, click OK. But before I get there, remember that if we have the entire population of interest, we stop right now. Right? We have an R square, we have a regression equation, which is telling us for every additional year of age, we expect the person's salary to increase by about $519. Now, even if we have the entire population, that's not going to be entirely accurate because our R square isn't that high. But That's the relationship we get, and we end there. Now, many times we have a sample of a larger population. If that's the case, that's where we start looking at significance right here and the confidence intervals. Kind of interesting, we actually usually don't worry about significance or confidence intervals of the constant or y-intercept. There are some cases where we might, but typically we're not. We kind of just ignore that, to be honest. But let's say that this is a sample and we hypothesize that there would be a positive relationship between age and salary. Well, we certainly did find that in a sample with a coefficient for age of $519. So can we make an inference that that's likely true for a larger population? Well, we get a significance of 0.00. Now, again, as I mentioned in class, it's not really zero. It's probably 0.0000 something. And if you click on it, you can actually, it will tell you. Here it puts it in scientific notation. It's a really small number, which is fine. But it's really small. It's less than the commonly used threshold for alpha of 0.05. So it's less than 0.05. So that's enough to reject the null hypothesis that there's no relationship and say that there is a relationship. If we're doing a one-tailed test, and our alternative hypothesis is that there's a positive relationship between age and salary, and that this coefficient should be positive. Well, there's evidence for that too. We got a positive coefficient, and it's statistically significant. So it's likely that in the population, the coefficient for age, the slope coefficient, might not be exactly $519, but it's probably going to be positive. That's kind of what that significance tells us. Personally, I like the confidence intervals. I like to interpret them. I think they're more useful than just looking at significance, because they really give us a range of what to expect in the population, which the significance by itself really doesn't. And so we get a 95% confidence interval for age, a lower bound of 376, and an upper bound of 661. I'm rounding. And so what's that saying is if we had the entire population of people, whatever our population is, I don't know what it is in this case. Is it like everyone in the U.S.? Are we just trying to make an inference to maybe a certain group of people? I don't know. But whatever that population is, how we defined it, we're 95% confident that the coefficient for age, if we had the entire population data, we ran the regression, we're 95% confident that that slope coefficient for age would be somewhere between 376 and 661. It's centered around the 519 we got in the sample. Again, in the population, it's likely not to be that exactly, but we're pretty confident it's within that range. And that just accounts for sampling error, the fact that the sample in the population, even if the sample is truly a probability or random sample, there's going to be some difference, particularly with a sample of this. This is not a particularly large sample. I forget the size, but it's not that large. So yeah, the population values might be different, but we still expect age to be positively related to salary. So that's an example of using a simple or bivariate OLS regression. Let's add some variables. And, this is the data set we use in class. We talked about, I'm going to leave this because we might want to compare our squares. We talked about education level. So when using regression, OLS regression, your dependent variable needs to be interval or ratio. And we're totally okay there because salary is ratio. Zero salary means you have no salary, a true meaningful 0 point. Age is ratio. Of course, it's our independent variable. We have a lot more flexibility there, but it's ratio as well. So our dependent variable must be interval or ratio. Independent variables, generally interval or ratio, but we can use nominal and ordinal variables if we code them correctly. And that's a big if. And I will warn you about this. I guarantee someone, probably more than one individuals in their projects who use education or some other variable will take something like this where we have someone's education level coded into 4 categories, and we'll look at what these are in their variable view. 1 less than high school, 2 high school, 3 some college, 4 college degree. And they'll take that variable and they'll put it in their regression equation as an independent variable, which just isn't right. It's just not the right way to do it. Yes, we can use ordinal variables as independent variables in regression, but we have to code them properly. All right. If you really want to make me upset, use it as a dependent variable, then I'll really go crazy. But even as an independent variable, we cannot just plug it in. We have to recode it. And we talked about this in class, recoding it into what we call dummy variables, zeros or ones. Is usually how I code the dummies. They're basically variables with 2 categories. You could code them 1, 2. I like 0, 1. 0 meaning you lack the attribute, and 1 meaning you have it. That makes the numbers a little more intuitive to interpret. If you don't know what they mean. But that's just me. So I'm going to take education level, and I'm going to code this into 3 different variables, representing the highest level of education a person has, starting with high school. Oops. Got that. And so if someone has a high school diploma, you got to think about the old values and what the new values would be. 1 means they have less than high school, so they don't have a high school diploma, so they get a 0. They have 2. That means actually a high school diploma is their highest level of education, so we give them a 1. If 3, that means some college, so high school is not their highest level, so they get a 0. And 4, having a college degree, they get a 0 too. And continue. High school is the name, and okay. By the way, you can screw this up sometimes, so you always want to check these afterwards. And what I do is I go back to variable view and I just move my high school one right next to my education level. That makes it very easy to check. And where I see someone with a 2 on education level, someone that has a high school diploma as their highest level of education, I should see a 1 for my high school dummy variable, and I do. For everyone else, I should see a 0. I'm going to go ahead and do that for the people that have some college and the people that have a college degree using the same function. I do have to change the names, and that's where you have to be careful and change the how I want it to code. Changing it to some college, all the new values. Not all these are going to change, but just for make it simpler so I don't get mixed up. Pull them all out and start with a 1, that would be 0. A 2, that would be 0. 3, people that have some college, they're the ones that get coded as a 1, and people as a 4 get a 0. And okay. And I'll check that in a minute once I do the final one, recode a different variable. I'm going to do it again, but this is going to be college. You have to make sure and change the names, and you have to make sure if you don't change the names, they'll just rewrite the old one with the new commands. So you want to be careful about that. I can actually keep some of these the same. 1 and 2 should still be 0. Now 3 should be 0, and 4 should be 1. Continue. Okay. Go back to variable view. I'm just going to move these so I can make sure they're right. And this is an important thing to do. Someone with an education level of 4, that means college. They have a dummy variable of 1 for college. The others are 0. Someone with a 2 has a high school. They're a 1 on their high school, 0 on all the other ones. And 3, we see we get a 1 for some college. So it all looks right. So I think we are ready to reanalyze and run our regression. Regression linear. Everything stays the same except we're going to throw in our 3 dummy variables. Now, you may find it odd I didn't create a dummy variable for the very first category for people that don't have a high school degree. And guess what? You can create a dummy variable for them. But you can't put, when you have 4 categories of education level, if you do create 4 dummy variables, you cannot put them all in at once. You'll have perfect linearity or perfect linear kind of relationship, and it won't run. Mathematically impossible, because you have to have something to compare to. And the coefficients, the slope coefficients we get for high school, some college, and college, are comparing the expected income of someone with those levels of education to someone without a high school. So it allows us to have something to compare to. You could alternatively create a dummy variable for someone without high school, and maybe not create one for someone with a college degree, or create it but don't include it in the regression. And then you would be comparing people without high school, people to high school, people with some college, to those with a college degree. But I think it's simpler to leave out the lowest level of education. It's a little more intuitive to interpret. So we get our results. Our R squared is way high now. It's about 82%. And you see our results here. Now we have 4 independent variables that we're using to predict salary. And our coefficient for age changed. And that makes sense, because when you add variables, you're now looking at the relationship between age and salary, holding education level constant. And if there's any sort of correlation between age and education level, that will tend to cause that coefficient to change once you hold education level constant. And we talked about this in class. It is kind of interesting. You see that we still have about, our coefficient for age is $293. So holding education level constant, we expect for every additional year of age, someone's salary to increase by $293. Looking at the coefficient for high school, we're saying someone with a high school degree, we expect to have about $5,339 in a higher salary compared to someone with no high school. For some college, we expect about $7,821 of additional income compared to someone without high school. And for someone with a college degree, we expect about $30,372 in additional annual earnings compared to someone without a high school diploma. Again, we're always comparing to that category that we left out. You can see looking here that for all our variables, we have statistically significant coefficients, so we can be pretty confident that if we had the entire population, we would get similar relationships that we see. We wouldn't get the exact same coefficients, but we would have a positive one for age and a positive one for high school, some college, and college. And then we have confidence intervals. So, and we talked about how to interpret those. They really don't change. Just if you're interpreting them, you also mentioned that you're holding the other factors constant. So if I'm saying, okay, I'm 95% confident that if I had the entire population, I ran a regression predicting salary, that the coefficient for age would be between $214 and $372, assuming I'm holding education level constant. That's the only thing that changes with that interpretation. All right, so that's OLS regression. In this case, multiple regression, because we have more than one independent variables. So with that, let's get into an example of logistic regression. I'm going to do the same one we did in class, if I can find it. Logistic regression data, that sounds right. And I'll probably pull up the Excel file too, because I don't know, sometimes what I have in the Excel file really does help with interpretation. You know, logistic regression is harder to interpret than our OLS regression. So just remember, why do we use logistic regression? And specifically, we're going to use binary logistic, okay? Like OLS regression, we can use any type of variable as an independent variable. Our independent variables can be interval or ratio. We can also use nominal or ordinal if we code them right. We have to code them as dummy variables, but we can certainly use them with logistic regression. With logistic regression, particularly with, and it's true for the other types, the difference is your dependent variable does not have to be interval or ratio like we have to have with OLS regression. With binary logistic, you have to have a dependent variable, and usually it's something that's nominal, or it might be something that's ordinal that we can break down into only 2 categories. We just have to have a dependent variable that we can put into 2 categories, whether you're self-employed or not, whether you have a college degree or not, whether you quit your job or not. There, of course, are other techniques for when you have more than 2 categories. Multinomial logistic is when you have more than 2 categories for your dependent variable. There are even things like ordinal regression when you have more than 2 categories and it's an ordinal variable instead of a nominal one. But we won't get into those because they are very complicated to interpret. Here's my data, whether they quit their job in the past year. I also have it coded as a number. I did this so I could run it in Excel. You can actually just use the quit variable in SPSS with the words attached to it. We have observation with just a person. We're not going to use that in age and salary. And just for interest, we're just going to take quit and look at it. Oops, yeah. Well, it'll like the number, I think. Actually, not what I wanted. Let's go to frequencies. And I think I can actually use the dummy there. Yeah. You say have 37 people, and what do we see? We have 0 and 1. 1 presumably mean they quit their job. 0 mean they didn't. 23 did not. 14 did. That equates to 62.2% that did quit their jobs, and 37.8% that 62.2% that did not, and 37.8% that did quit their jobs. All right. So logistic regression can allow us to predict who quit. And using the variables we have, it'd be great if we had more, but in this case, we just have salary and age. So linear, we do not want to use. We want to use binary logistic. And I'm going to put quit as my dependent and age and salary as covariants. They're independent variables. There's some other options too that we have. If we have a categorical independent variable, we can put that there. There's some other options, but I usually don't select much else out of here. Click OK. And here's our results. It starts with this first classification table, which tells us how it would predict whether someone quit or not if there was no information. We know 62.2% of people did not quit. So if you had to guess if any one person quit, you'd say they did not quit, right? And that's exactly what SPSS does. It takes everyone, and it predicts that they did not quit. And for 23 of those people, it's correct. For 14, it's incorrect because 14 of them did quit. So it's right 62.2% of the time. That's just to give us a baseline and figure out, if that you could get this good by just saying everyone did not quit. So you're not really. It sounds good. You got 62% right, but it's not really a big accomplishment. It's the baseline. It's what anyone could do by just predicting everyone did not quit. Right. Anyways. Kind of like the UP in January. If someone asks you to predict whether it's going to snow tomorrow, it's not 50-50. You'd probably say, yes, it's going to snow tomorrow, because you'd probably be right 80% of the time by just saying, yeah, it's going to snow. It's kind of the same kind of idea. The other things that are very useful are the other classification table, which actually shows us when we throw in our salary and our age variable, how accurately we were able to predict who quit. And you see that it was a little better. Got 78.4% of the predictions right. Not 100, but better than the 62.2% we got by just kind of saying everyone did not quit, or predicting that none of the people quit. We have predicted on top, observed here on the side. 20 people did not quit, and we predicted they did not quit, got those right. 9 people quit, and we predicted they quit, got those right. We have 3 people who did not quit that we predicted did quit, got those wrong. We have 5 people who did quit, we predicted they did not quit, got those ones wrong too. And these predictions just come about. If you actually do the math, the logistic regression will give you a probability, and if it's greater than 0.5, you predict that person's going to quit. If it's less than 0.5, you predict they're not going to quit. And you'll see that in the Excel file if you look at it, because I actually did the math. Now, as I mentioned in class, the tricky thing is with doing the math is you can't just take the coefficients here like you can with regular OLS regression and start predicting probabilities. You can't just say, okay, our y-intercept, our constant of 2.913, take that, add to that the coefficient for salary, which is actually a positive 0.00014 times their annual salary minus 0.102 times their age. It doesn't give you the probability of quitting. That's kind of the starting point, but you actually take that and do some mathematical manipulation to turn that to a probability, which if you want to examine, you can look at my formulas in the Excel file, but I'm not going to get into that here. But it does tell us a couple things. It tells us, number one, what's statistically significant. It tells us the direction. Again, the salary is not actually 0. If you click on it, you'll see it's a positive 0.00014, which shows us in our sample we have a positive relationship between salary and quitting and a negative relationship between age and quitting. Okay, are they something we would expect in the population? Well, age is statistically significant, so yeah, we are likely to have a relationship in the population. With salary, it's not statistically significant. So in the population, there might be a negative relationship, there might be no relationship. We really don't know. So that's really about as far as you can interpret. You also do get the pseudo R-squares. There's a bunch of different ones. SPSS gives you 2. They're kind of like an R-square, percentage of variance explained in the dependent variable by the independent variables, but they're not quite equivalent. That's why they're called pseudo R-squares. But they do give you some idea of how well you're able to explain whether someone quits. Although this classification table compared to the original classification table is sometimes a more intuitive way of looking at that. All right, so I think that will be it for regression.